Hello again, students. Today we're going to do an introduction to linear programming. So this is going to tie basically all of our systems of equations and inequalities unit together just to a really big application type problems. So linear programming is a mathematical process that uses linear functions to solve certain kinds of optimization problems. So what I mean by optimization, you're trying to either get the most out of something or the least out of something. Linear programming actually came about back during World War II when they were trying to figure out where was the best place to allocate weapons and supplies during World War II. And we still use it to this day. So we will either find a maximum or minimum value of a function over a region. And some vocab that you need to know are constraints. Those are the inequalities that serve as your boundaries because you're not going to have unlimited supplies. You're not going to have unlimited access to things. So there are going to be some constraints which you'll need to take into consideration. Once you've graphed those constraints, where all of those constraints overlap, that's what's called the feasible region. All right, so that's the intersection of the graphs of the inequalities. And what some mathematicians a while ago discovered is that the best solution will always be at one of the corner points of those feasible regions. And so then what you do is you take your corner points and you plug them into what's called the objective function. So the objective, what are you trying to do? What's the goal? All right, so a lot of times it's going to deal with something like maximizing profit or minimizing costs and things like that. So you see this a lot in the business world. All right, so what we're going to do for this lesson is we're just going to look at the how-tos. So we're not going to put it all together with the big word problems and do an entire problem today. Instead, what we're going to do is we're just going to be doing how you do it. All right, so just looking at the given constraints and then looking at the feasible region and figuring out the maximum or minimum of the objective function. And we're also going to set up the problems. And then in the next lesson, we're going to put it all together. All right, so in this first example, it tells us that the objective function is to take 3 times some value plus 4 times another value. All right, so we don't know, we don't have any background for what this means. All right, but we do have an expression. Technically, it's an equation because I have it set equal to 0. All right, we are trying to find a maximum value for that. All right, so we have an infinite number of points that we could plug in for x and y. But we're going to limit those points based on these constraints. All right, so what we need to do is we need to graph these constraints to start off with. All right, so application problems, you're almost always going to see these two constraints right here. All right, these two constraints right here. Why? Well, because if we're doing application problems, you're probably not going to be able to have negative values for whatever your variables represent. All right, so what this means is that we're just going to be in quadrant 1. All right, so think of a coordinate plane, quadrant 1. Okay, that's in your upper right-hand corner. All right, so to the upper right-hand of the origin. All right, so there is part of the x-axis from the origin and over, and here's part of the y-axis from the origin and up. All right, so this line right here, okay, right here, this is a horizontal line, so this would represent the inequality y is greater than or equal to 0, except for technically it'd be all of this part that's above it. And then x is greater than or equal to 0. Remember, x equals a number, that's a vertical line. Okay, so that's this constraint right here. And again, greater than or equal to 0. Right, but you're not actually going to shade all of that. Just know that these two inequalities means that you're limiting your problem to just quadrant 1. All right, the other two inequalities have both x and y in them, which means that these are going to be slanted lines. You have a couple ways that you can graph them. All right, so one way you could graph them would be 2x plus y is less than or equal to 4. You could do intercepts. All right, so I could find my x-intercept. Remember, to be on the x-axis, it means that y is going to be equal to 0. So in this inequality, if I plug in 0 for y, that give me plus 0 is less than or equal to 4. That'd give me 2x is less than or equal to 4. Divide both sides by 2, I get x is less than or equal to 2. All right, so my x-intercept would be at 2. And then likewise, I could do my y-intercept. and to be a y-intercept, that means the x-coordinate's 0. And so then I plug in 0 in for x, so that'll give me 2 times 0 plus y is less than or equal to 4. This cancels out, so y is less than or equal to 4. So my y-intercept would be 4. All right, so then I can plot those points. Okay, it's a very good idea that you come up with a scale. So in this case, okay, I'm working with small numbers, so I can just go by ones. You do not have to go by the same scale on your x and on your y-axis. However, if you ever plan to use slope, then you have to have the same scale. All right, so if I'm just plotting x-intercept and y-intercept, my scales don't have to match. But if I wanted to use slope, they would. I'm going to use slope with my second inequality up there. So I am going to go ahead and make my scale match. So I'm just going to go by 1. So this would represent 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And likewise, this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right, so plotting this one up here, 2x plus y is less than or equal to 4. I'd plot on the y-axis a point at 4, and on the x-axis I'd plot a point at 2, and then I'd connect these with a straight line. All right, and since my inequality says or equal to, I know this boundary line is included, so it's going to be a solid line. So I'm going to simplify this a little bit. I'm just going down 4 and to the right 2. So 4 over 2 can simplify to 2 over 1, so that means that I could put another point right here. All right, and then the best that I can, I'm going to connect those. All right, now my other inequality, let me get a different color here. My other inequality, I have negative x plus y is less than or equal to 1. I'm going to graph this one using intercept form, slope-intercept form. So I'm going to move the x term over by adding x to both sides. It's going to give me y is less than or equal to, I'm going to squeeze in the positive x first, and that was a positive 1, so that's a plus 1. And so my slope is 1 over 1. The number in front of x is it's not there, which is an implied positive 1, so I write it as a fraction, and my y-intercept is 1. All right, so on the y-axis, sorry, that doesn't look like a 1, it's a 1. I plot my point at 1, and then I move up 1 to the right 1, up 1 to the right 1, up 1 to the right 1. All right. So all of these are points on that boundary constraint right there. And because it says or equal to, it means that they would be included in the solution. So the best I can, I'm going to connect these with a solid ray. All right, so now what I need to do is notice that this quadrant has now been split into 4 regions. You have this region down here, you have this region over here, up here, and over here. All right, so 4 regions. We need to figure out where all of the overlap would be. All right, so really what we need to look at are these 2 inequalities right here. All right, so we have 2x plus y is less than or equal to 4. The easiest way to do this is I'm going to use a test point. All right, so I'm going to use a test point, so TP for test point 0, 0, because it's not on the boundary line. All right, so that's going to give me 2 times 0 plus 0 is less than or equal to 4. So 0 is less than or equal to 4. That's true, which means I'd be shading where 0, 0 is. So that'd be this triangular region here. All right, but then this other constraint, the one that I graphed in green, splits that triangular region into 2 other pieces. So now we need to figure out, okay, for the other constraint, where are we going to shade? So I need a test point for it. So once again, I'll choose a test point of 0, 0. So plugging it into this inequality, I get negative 0 plus 0 is 0 is less than or equal to 1. That's also true, excuse me. So because it's true, here's where 0, 0 is. So here is where my feasible region lies. All right, so let's look at that feasible region. All right, so it goes from here to here, here to here, here to here, here to here. So it has, okay, it's an odd-looking shape. Okay, it's not a regular shape. By all means, it's definitely not regular. It's definitely irregular. All right, but we have 1, 2, 3, 4 sides. All right, so the feasible region has 4 sides to it. So because it has 4 sides, it also means that it has 4 corner points. And like I said before, a mathematician back during World War II discovered that the best solution is always going to be at one of the corner points of that feasible region. So in this table, we're now going to identify the corner points. All right, so one of the corner points is 0, 0, right here. Another point right here is, this is the x-axis, that's 2, 0. where they overlapped, or where they intersected is what I should say, the two inequalities that were slanted, those intersected at the ordered pair 1, 2. And then 0, 1 for the final corner point. All right, so then what you do is you take your corner points and you plug them into the objective function. All right, so remember in an ordered pair, you have your x followed by your y. So we're going to take 3 times the x plus 4 times the y, which 3 times 0 plus 4 times 0 is 0. We'll take 3 times 2 plus 4 times 0. That would give us 6 plus 0, which is 6. We take 3 times 1 plus 4 times 2, which is going to give us 3 plus 8, which is 11. And we take 3 times 0 plus 4 times 1, and that's going to give us 0 plus 4, which is 4. All right, so the objective before was to maximize this expression. All right, so we're going to try to maximize the maximum value out of the numbers that we got was at 11. All right, so what this tells us is that the max value, so the maximum value is 11 when x is 1 and y is 2. All right, so we really don't have any background behind this. Okay, we don't know what x is, we don't know what y is, we don't know what we're maximizing. All right, but this is how you do these types of problems. You come up with your constraints, you come up with your objective function, you graph your constraints, you figure out your feasible region, you take only the corner points of the feasible region, you plug those into the objective function, you get these outputs, and then you look for either the highest value or the lowest value, depending on if you're trying to maximize or minimize. All right, so now let's look at how the problems are going to be presented to you. Big word problems. All right, so what you should do is read through the question, ask yourself what the problem wants you to do, and then you're going to come up with the objective function, also going to need to define your variables. All right, so what are those unknowns that you could change? And then also come up with those constraints. All right, so this says a theater is presenting a program on drinking and driving for students and their parents or other responsible adults. The proceeds will be donated to a local alcohol information center. Admission is $2 for adults and $1 for students. However, this situation has two constraints. The theater can hold no more than 240 people, and if less than 30 people sign up, the event will be canceled. How many adults and students should attend to raise the maximum amount of money? All right, so right here, how many adults? The last question, the last sentence, the one that has the question mark, gives you a lot of key information. It says how many adults and students. Okay, so that's the number that can vary, the numbers that can vary. So those are going to be your variables. So if you're asked to define your variables, in this case, pick a letter. I'm just going to use the common x and y, especially since eventually we'll be graphing, so it'd be a good idea to have your x-axis and your y-axis. I'm going to let x represent the adults, but I'm not just going to put adults. What about the adults? Is it their age? Is it their weight? No, it's how many adults. All right, so x is going to represent the number of adults. If you want to be really good, you'd say the number of adults in attendance. Y is going to represent the number of students. And I could have reversed those if I wanted to. Okay, then the sentence also gives me one other key information. It says how many adults and students should attend to raise the maximum amount of money. Remember, this is for, they're going to donate the proceeds. So this is a fundraiser. All right, it's just good to have in general, but it is a fundraiser as well. All right, so they're going to raise, they're trying to raise the maximum amount of money. That's the objective, is raise the most amount of money. All right, so what we need to do is we need to go back through here and we need to figure out, okay, what's the money? Where's the money going to come from? All right, and so if you're going to be having a program, okay, you're going to be making money off of the admission. All right, so it says the admission is $2 for adults and $1 for students. All right, so $2 for adults. So 2 times however many adults there are. Hey, we have a variable for that. So that's going to be 2 times x plus $1 for all of the students that are there. All right, so here is going to be what's called our objective function. This is what's going to give us how much money they make from this program. All right, now, there are some constraints. Let's do the two easiest ones first. If x represents your number of adults, you can't have a negative number of adults, so x is going to have to be greater than or equal to 0. Y, likewise, is also going to have to be greater than or equal to 0. Remember, these constraints are just restricting us to the first quadrant. Okay, I've already used this value, I've already used this value. Now I'm going to go back through, I'm going to pick out other numbers. So I'm scanning, this is all good background information. However, this situation has two constraints. They're nice in this problem, they're telling us that there are two constraints. That won't always happen. The theater can hold no more than, all right, so no more than. So if X is the number of adults in attendance, Y is the number of students attendance, together there can't be any more than 240 people. So there could be less than 240 people, or there could be equal to 240 people. The other constraint deals with the other number, which says if less than 30 people sign up, the event will be canceled. All right, so that means X plus Y, if less than 30 people sign up, the event's going to be canceled. So that means that there needs to be more than 30 people. Less than, it'd be canceled, so 29 would be canceled, but if you had 30, it would still go on. So I'm going to put an or equal to here. All right, so here is the setup for my problem. Okay, if I were to actually continue this problem, I would then graph these constraints. I would look for the feasible region where all of the shading overlaps. I would look only at the corner points of that feasible region. I'd plug them into this objective function, and then I'd look for my maximum value. All right, let's do another one of those examples. So a landscaping company has crews who mow lawns and prune shrubbery. The company schedules 1 hour for mowing jobs and 3 hours for pruning jobs. Each crew is scheduled for no more than 2 pruning jobs per day. Each crew's schedule is set up for a maximum of 9 hours per day. On the average, the charge for mowing a lawn is $40 and the charge for pruning shrubbery is $120. Find a combination of mowing lawns and pruning shrubs that will maximize the income the company receives per day for one of its crews. All right, so once again, it's that last sentence. Almost always, that's going to give you a lot of key information to help you start to set up. So find a combination of mowing lawns and pruning shrubs. All right, that's going to be our variables. That's what whoever's deciding the schedule for the day, that's what they can change, is going to be the number of lawns mowed, and Y will be the number of shrubs pruned. Okay, that's what the company has in their control, how much they schedule for a day. Their objective, so the objective function, their objective is to maximize the income. If this is your business, you'd probably want to be doing the same. You're trying to figure, okay, how can I make the most amount of money? What's going to be what's going to be possible? All right, so the objective is to maximize the income. Income, again, you're working with money, so go back through and pick out what deals with money. It says the charge for mowing a lawn is $40. That's $40 times however many lawns are mown, which is X. But they can also make money off of pruning shrubbery, which is $120 times number of shrubs pruned, which is Y. All right, so now we need to come up with what are called the constraints. All right, because there's only so much time in a day. You can only have your workers work for so much time in a day, and so on. And you also need to consider the machinery that you might need. Okay, maybe you can't have 5 people mowing lawns because you don't have that many lawnmowers, and so on. So there are going to be some constraints in this situation. First constraint, you're not going to have any negative number of lawns or shrubs. So we're going to have X is greater than or equal to 0, Y is greater than or equal to 0. All right, now I'm going to go back through and I'm going to pick out the numbers. The company schedules 1 hour for mowing jobs, 3 hours for pruning jobs. Notice that unit of measure is hours. So 1 hour, 3 hours. We're talking about time. All right, so there's going to be a constraint for time. So it's 1 hour for mowing jobs. So that's 1 times however many mowing jobs there are. Plus, they also have to do pruning jobs, and that's 3 times however many pruning jobs there are. This number right here tells us how many pruning jobs they can do. It's not dealing with hours. So I'm going to continue on. And here it says each crew's schedule is set up for a maximum of 9 hours per day. So that's going to go into the time constraint. They have a maximum, so that means they could work less than 9 hours or equal to 9 hours. On the average, the charge for mowing, we already used those numbers. So there's only one other number I haven't used yet. Each crew is scheduled for no more than 2 pruning jobs per day. All right, so number of pruning jobs, that's Y. We're talking about 2 per day. No more than 2, which means that we could do less than 2 or we could do equal to 2. All right, so we've now used all the numbers, we've used all the background information, we know what we have the capability of changing, we know what we're trying to do with them, and we now know what we're limited to. And then we could put it all together and we could come up with an actual answer for how we should schedule this company's workday. All right, so I hope this video helps with setting up linear programming problems. In the next video, we are going to actually do a full linear programming problem where we're going to put it all together.